Good evening, everyone. Welcome to Stony Brook University School of Marine and Atmospheric Sciences Spring Lecture Series, lecture number 2. I'm Chris Gobler, and I'm the Director of Academic Programs for SOMAS, School of Marine and Atmospheric Sciences, here in Southampton. And it's my pleasure to be co-introducing to you tonight's speaker, who is, of course, John Bouvier. But I'm going to actually pass it over to Donna McCormick from the Montauk Observatory, and she'll tell you a little bit about their role in this lecture.
I'd just like to thank you all for coming on this very wintry night, and thank Chris and the School of Marine and Atmospheric Sciences for co-hosting this. Montauk Observatory, we've been around since 2005. And our mission is to foster interest in science, especially astronomy, throughout the South Fork. So what we've done toward that end is we have a little astronomical observatory on the campus of the Ross School in East Hampton. We're still setting it up, but once we're up and running, we're going to have not only people coming through to look through the eyepiece, but also it'll be accessible over the internet. So students and educators and researchers and everybody can log on and use the equipment to do their projects, view the night sky. We also hold lectures like this one at different nonprofit venues throughout the South Fork. And that's why we're exceedingly grateful for having the opportunity tonight to be here. We are a nonprofit. We've been handing out flyers here. If you have any questions, you can see me after the talk. I also have some email slips if you're not on our mailing list but would like to be. They're out there. So any questions, let me know. And again, we'd like to also thank John, who it was very kind of him to come out of a kind of retirement to do this lecture tonight. I'm certainly excited to hear all about it, and I hope you are too. But I'll turn it back to Chris for more information.
Yeah, so before I introduce John as our speaker, I'll just mention that I said already this is part of our spring lecture series, and I'll emphasize the next lecture should be very exciting. It's by me. So I encourage you to come to my annual State of the Bays Symposium. It's actually a very fun event. It involves probably about a dozen graduate students who are doing research here in Southampton. We'll be talking about their research and what they're finding in our local bays and estuaries with regard to resident marine life, fisheries, and also resident habitats. So they'll be presenting posters out in the lobby from 7 to 7:30 on that night, and then I'm going to give a 1-hour seminar with regards to the state of our bays. And then when that ends, there'll be another opportunity to again speak with the students. So it's usually a very fun event, very interactive, and you get to learn about the state of our bay. So I encourage you to come to that. That's the first Friday in April. I can't remember the precise number. What does it say on the flyer? Somebody have that date?
Well, the 12th is a Friday. We're having a lecture on the 12th about the moon. We'll have observing telescopes set up. That's going to be at SOFO, so I guess it would be the 5th.
The 5th, okay,
Yeah.
So April 5th. So, but with that being said, tonight's speaker, of course, is John Bouvier, who we know as town council member here in the town of Southampton. I've always known that has and always had and currently has a deep love for our oceans and marine waters. He's a diver and has a great appreciation for our local waters. But I did not know, until I was contacted by the Montauk Observatory, that in his former life, not only did he have an appreciation for the marine waters, but recovered things from the deep sea. So I guess I'll leave it to him to explain it, but we're grateful he's here, and it should be a very interesting lecture. So thank you to John, thank you all for coming, so take it away.
All right, thank you. So I have to say that I'm generally a pretty private guy. I'm going to be talking about things that happened 35, 40 years ago. Donna, who just went to the corner, I blame her if things go wrong. She's an unbelievably persuasive person, and I find myself standing here and see a lot of friends. And thank you all so very much for coming out on a Friday night, on a wintry night, to sit here and listen to me talk about my life. I didn't realize, sort of a nostalgic moment for me, going through these things. I've gone through slides and stuff. This is stuff I hadn't thought about for 35 or 40 years. So it's been kind of an interesting voyage for me, and I'll probably wax philosophical on occasion. And certainly I have a lot of sea stories, so I've asked Donna to give me one of these, because anybody who knows me here knows that once I start rolling, I can't stop. So can you all hear me all right? Okay. So we're going to get started. So at the risk of personal and professional embarrassment, I'm the little guy there, 4 years old. This is how I started. This is where I started wanting to be underwater. It just came naturally to me, and I grew up here. I grew up in Remsenburg, and we went to the bays, and we got clams and scallops, and we did all that kind of stuff, and that's how I really had this hook in my heart to start exploring. I ended up, when my family moved to Europe, I came back. As a long story short, I went to high school here, and instead of going to college, at first I went to dive school because I wanted to be like Jacques Cousteau. I grew up with Jacques Cousteau, and I thought, man, he's cool. I want to be just like him. So he was my childhood hero. So I did go to dive school, and I did a lot of dive work, saturation diving. I worked for the oil industry, which I thought was kind of I didn't know what to expect, but I had to make money. And so I traveled for quite a few years, taking contract jobs as a diver, worked scraping container ships, the bottoms with spatulas. I worked on all sorts of different outfall pipes, which is a messy job when you're a diver. I studied deep sea diving and with DESCO systems, saturation, which we'll get into, and we'll talk a little bit about these things as we go along. But I look at this and I realize, wow, a lot of time has gone by. And I didn't recognize myself, and my daughter sort of screamed when she saw that. She didn't really. So we'll keep moving. And I apologize if this is a little over an hour. I'm going to try to shorten it, I know, because the weather's coming in and I want to have time to take questions. So a typical saturation system is the bell that you see there. You live in this, and you come up from the depths, usually around 300-400 feet, typically on saturation. And then you spend your time in the chamber, and you have 2 other friends or 3 other friends that you either learn to hate rapidly or love rapidly. And you spend a lot of time, typically 14 days underwater is typically what I spent on that. We'll talk a little bit about that as we go on. So typical, yes, that's me hidden in there someplace. This is actually this became an ad somewhere, but that's the typical saturation dive. We use a mixed gas. We'll talk about that as we go forward. I'm going to make comparisons between going deep underwater and going up into space. And we'll talk about that as we go forward. So one of the jobs I had was working on the DSRV, the Deep Submergence Rescue Vehicle. That was one of the first projects that I got involved in. These systems are used for rescuing divers or submariners from ships, subs that sank on the bottom. But they're also used for covert work. That's typically how they operated. And I gained a lot of exposure from doing that work. And I joined DARPA with the Angler program. It's called the Angler program today, but this was my first exposure to robotics. And I learned a lot about that. It's a really wonderful organization. It was actually started out as the Advanced Research Project Agency, then it went to the Defense Department, then it went back. So I sort of stepped in and out of different agencies, defense agencies and different things like that. After that was about 7 or 8 years, I met somebody named Sylvia Earle, who I think Maria is here, who knows. She's a very well-known marine biologist. She's known as her deepness, very famous. She's a really incredible person, and she made a huge impression on me. And the way I met her is I went to Syracuse to see a lecture, and 20-something years old, I just went up to her and I talked to her, and she invited me to California on the spot. Because what she was doing with a guy named Al Giddings, you may know his name, he was a guy who filmed The Abyss. And he wanted to be the next American. He wanted to be the American Cousteau. So he bought this ship. It was an old mine ship. He wanted to convert that. So little did I know at the time, when I was so honored that Sylvia invited me, that there were 20 other people that she had invited so that we could all work on this ship and rip the engine rooms out and tear it apart and make it and turn it into a research vessel. We put a saturation system on board, and it was a great 3-year period of my life. It was really amazing with just a lot of good people and a lot of fun. That's Sylvia. Sylvia, Graham Hawkins, and that's another young version of myself. What we did after Sylvia separated her relationship with Al Giddings, she met Graham Hawkins, who is the designer of one-man atmosphere submersibles, which we'll talk about in a minute. She was an amazing, she made such an impression on me. So during this sort of nostalgic trip I've taken about my past, I realized that there were these individuals who made such a difference to me without me realizing it and without me appreciating it until this very night, or the few weeks preparing for this. That is a seawater hydraulic robotic system that Graham and I designed in that building behind there. This was Sylvia Earle's house in Oakland, and this was the garage that we worked at. And we built these things there. And that led to the design and development, you'll recognize the robotic systems, of Deep Rover, which is a one-man, one-atmosphere system. That's an acrylic sphere. It's about 12 inches thick. It's rated to 3,000 feet. And it was my real first exposure to submarines in a truest sense, not being able to look through a little porthole, but being able to look out of a giant dome. And just for full disclosure, my design was here. That was my claim to fame at the time, but also seawater hydraulics. So we'll talk a little bit about the water pressure, but as you go down, you get more pressure, obviously. So the SIS system worked on pushing the robotic arms forward, but using seawater pressure to drive them back. So you didn't need to go back and forth. We used the seawater pressure. So the deeper you go, the more powerful these robotic arms became. And this was in the, I guess, middle 80s, no, late 70s actually. So this was really advanced stuff for its time. It was just an incredible opportunity that I had. I just stumbled into this. I learned so much from that man, Graham Hawkins, and from Sylvia Earle, who was probably the person who planted the seed in my head that instead of being underwater working for the energy industry, that I wanted to do what I'd really set out to do, and that was to be an explorer. And I would say that arguably she was one of the greatest explorers, and not as well known as she should be. She's now in her 80s, still active and vibrant, and I love her to death. That's me again, Donna. Donna wanted personal photographs on occasion to put in, just so that this is a test in Port Hueneme. In order to put a vehicle underwater, we have to test it to 4 times its rated depth. So that was a 3,000 foot system, so we had to pressurize it to 12,000 feet in this vessel. That's the top of it up here. Oops, that's the top of it. And so I'm hooking up the monitoring lines, and then you see all these are bolt holes, that closes down on top of it. This is the acrylic hull, it's just got protection on it. And so that was quite an experience to pressurize something to 12,000 feet, and you're standing next to it and you're hearing it creak and groan, and that was an interesting experience for me. So compare that, the great pressure, to what you do in space where you have no pressure. You have a vacuum. So satellites and vehicles in space are also tested, but they're tested for being in 0 PSI. And this might be a good time to talk a little bit about that, sort of a quick physics 101. We're right now experiencing 14.7 PSI, that's pounds per square inch. So if you can imagine a column of air going into space where there's no more air, that column weighs 14.7 pounds to sea level. And so you're all experiencing that pressure. As you go deeper, every 33 feet, you add another 14.7 PSI. And you can imagine as you reach the bottom of the ocean, the greatest depths, you're experiencing somewhere at the Marianas Trench well over 16,000 PSI. That's 16,000 pounds of pressure on every square inch of that vehicle. Now, if you go the opposite way, you go up your atmosphere pressure goes down. So you start to go up 10, 15,000 feet, you're at about 12 psi, 10 psi, something like that. And that's significant of what we'll talk about later, because that's the pressure that astronauts perform their EVAs under. And there's a reason why they perform it at less pressure than standard pressure that we experience now. And if you have any questions, just throw it out. I like conversations. I'd rather be sitting around a table with you all and talking about this stuff. So we also designed a system called Rig Rover, which has the seawater hydraulics, and you'll see here. I'll get this by the end of the presentation. This is a tugger. It's an air hoist, and then control things. We'll move on. I know I'm probably not going fast enough. This is on a typical oil rig. This is a Rig Rover going down. These things here are guide wires. This is the drill string. This goes down. That's what collects the oil. The oil comes up through it through something called a blowout preventer, and I'll explain that in a bit. Typical oil rig, these are the things that I worked on prior to joining Sylvia Earle and Graham at Deep Ocean Engineering. I worked around the world on semi-submersible oil rigs like this, from exotic places like the coast of Nigeria, where they had a war, which was comprised of a Cessna with a guy with a bomb, and he'd drop it out, and then they go away, and this was the kind of environment that we were in. Yeah, it was interesting. And I won't go into that. If you have any questions on semi-subs, we'll get to that. But I do want to make a point that underwater, the things you don't see are these vast complexes that are built that most of the time we don't see. This is a directional drilling system. So you have multiple wellheads, and they're drilling into different directions. So to give you an idea of the scale, that's a person, to give you scale. And this was the moment when I had a great realization that I didn't want to do this anymore. And the reason is I was asked, I observed a leak, and I was asked to qualify or characterize the leak. So how do I do that? I use a bucket, and I measured drops of oil that went into the bucket over 15 minutes, and I determined that the leaking was about 1 gallon a minute. And I called topside. So when you're underwater, you're a diver. You're the diver, whatever your number is. On the top, you talk to topside. I said, topside, I'm getting about 1 gallon a minute. And the answer I got was, that's okay, it's within limits, don't worry about it. That was the moment I changed total directions in my life. I left this and I never went back. I went to space station instead. And the way I got there was, again, one of those fortuitous moments in your life. I was asked to join flight tests at Grumman here in Calverton. And I wanted to come back to New York. I had missed my parents. I hadn't seen family. And it seemed like the perfect opportunity. And I'd learned how to fly. I convinced my company that for me to do these kinds of things, I had to get a pilot's license. So the three of us got pilot's licenses, and that's how we ended up here. But about 2 months into that, I was asked to join the space station program with Grumman because of my background in robotics. I became lead engineer for robotic systems on space station, and I worked at Goddard. I worked at headquarters. We did a lot of work with robotics, and we'll talk a little bit about that as we go forward. I worked on the original concept for space station, which was called Space Station Freedom. This is it here. Just to give you an idea, the pressurized parts of this are equal to the volume of a 747, and it's in standard atmosphere, nitrogen atmosphere, just like we're breathing now, 20% oxygen, 80% nitrogen roughly. That's what we're breathing right now. That's the same atmosphere as on space station. So you can see how it evolved into what you know as the ISS, the International Space Station. And the reason for that was that they started to run out of funding. And I remember testifying in front of a subcommittee when I had a senator say, well, how can we make it look the same, but it costs $500 million less? And we said, move farther away. So the first three systems that were on there was the Flight Telerobotic Servicer, which was developed at Goddard, and its idea was to have these three little arms crawl along the truss of the space station, sort of hand over, foot over hand. That was their concept. oddly enough, just today or yesterday, SPAR, which is the developer of the robotic arm on the shuttle, that was on the shuttle, the one on space station, has a contract for what's called the Canadarm3, which is sort of like that, that was actually abandoned for something called the SPDM, which was a sort of, you'll see the sort of similarity between those two. These are the two main systems. This one went away. This was the SPDM with the main arm, and this is the Japanese experiment module. So out here, this is exposed to space. They would do experiments, and then this arm would bring those experiments into the habitat. And this was my area of responsibility. So this is how it went from paper to reality, and it's pretty cool. You'll see, talk a little bit about, we'll go here. This is the experiment module, and you'll see that there's a lot of similarity, there's a lot of similarity between the tool interfaces. If you see all those round things, those are tool interfaces. So dexterity is a really important issue. We have the same problem in space as we do underwater, being able to use your hands. So a lot of energy goes into developing manipulators that have that same capability. And it's not as easy as it sounds, and certainly isn't perfected. And that's why we developed an interface that allows those robotic systems to find a common grapple point. That's what it's called. So how do you control those? Well, all sorts of ways. People have been trying mind control, but the real truth is that you want to control a robot. So this is my arm. I want to take this point and I want it to go here. But you have to calculate all the angular changes and how you get that. You also have to make sure that those angular changes don't interfere with something else. It's not as easy as it sounds, and sometimes things go really wrong. This is an ergonomic controller to try to simulate that. This was early work. Remember, bear in mind, this was about 35 years ago. So we were pioneering a lot of the technologies that have been advanced today. This is the Canadian Space Agency Control Center. It's actually in Canada. So they can upgrade, they upload the commands. It can actually be commanded from the ground, but they also upload all the maintenance upgrades. So the original arm on Earth can't hold its own weight. And they can upgrade that by changing some of the rates and some of the issues regarding spindle speed. And I'll take questions afterwards and we can talk about that. But it's kind of cool that they can do that. So we also worked on Hubble, and I'm not really following my own notes, so I apologize. I'm just talking from memory, and I apologize if I'm talking fast, but I know everybody wants to get out of here. This is the Neutral Buoyancy Lab, and you can see the dimensions of it. It's about 6.2 million gallons of water. And it's probably the closest you get to simulating gravity, but it's not really simulating gravity at all. You're in an environment where you still have the drag of the water. Anybody who's swum through water, you can't really go. You also still experience gravity. So if you're in your spacesuit and you sort of turn sideways, you're pushing against the gravity of the suit. So if the suit doesn't fit properly, you're kind of sitting on the bottom of a suit, and you can't really do much because you're being pressed against the suit, which is still buoyant. And it's not a great simulation, and most astronauts tell you it really is not a simulation at all. But it's a lot of fun to do. So early work, that's Donna for you again. That's me in here, I tell you. This was early work that we did in the Neutral Buoyancy Lab on designing tools to how to move modules and things along space station. So we had to test reach, and this is before, and Raymond knows this is before really good graphical ability to do reach studies and things like that. Not very sophisticated. Computers did not really exist that had those kinds of speeds, or certainly they weren't used. So we had to do a lot of practical testing, which was great. I loved it. I love that. I'm kind of sorry that we're going to simulations, because I like the empirical stuff. I like to do the real stuff. It was a really interesting experience for me. It was the one and only time I did that. And I toyed with the idea of joining the astronaut program, but I didn't. Oops. So another way to simulate gravity is using an aircraft. And the aircraft, this is a KC-135. It goes up at about 45-degree angle. And you can see it flies a parabolic course. So as you go up this path, as you go over, you go nose low. At this point here, you have about 20 seconds, 25 seconds of simulated weightlessness. And you really are. You're floating around, and which way is up, you're nauseated, and you're worried that the person next to you is not more nauseated than you. And then you come back to gravity. And the reason it's called the vomit comet is, if you'll notice, there are a lot of stains along here. And it does happen, trust me. Not me, no. We also, a fourth way to train astronauts was using vehicles. This is the Mantis, the gentleman I talked to you about, Graham Hawkes, before. This is his design. It was originally designed for offshore oil work, but we turned it to University of California at Santa Barbara. They used it as a research vessel, research submarine. It had about a 1,200-foot depth rating. But there was an astronaut, and I'll skip over that, Roberta Bondar, who was the first Canadian woman in space. And she thought that that would be a good idea to train astronauts using the submarines. I think it's just because she wanted to go learn and hang out with the submariners, and we had a great time. It's the same excuse that I used to learn how to fly. You know, I thought, hey, I want to do this other stuff, so I'm going to learn how to fly, and she wanted to learn how to use a submarine. She was a really great person. And she actually opened this up. We had a number of astronauts actually do this. Story Musgrave is the guy in Hubble, we'll talk about that, who actually trained with us. It was just a lot of fun. Nobody knows this, probably, I don't think, but today is the first day of National Women in Science Month. And I want to give a shout out. This is a group photo of all American astronaut women in space. That was taken a few years ago. It's a very cool group of people. I've had the great fortune to meet a few of them, and I got to say honestly, probably better astronauts for a lot of reasons. But what a wonderful, wonderful group of people. We worked on the Hubble Space Telescope. As you know, the Hubble had an aberration in its mirror. I think it was in. If I go look at my notes again. I forget the year. Well, I don't have the year here. I think it was 1998. I think was when the first mission. There were 5 missions that were done to repair the satellite. The reason that's important is that the Hubble Space Telescope was the first telescope actually designed to be serviced on orbit. So when you design robotic systems, you really want to have something that you're working on that will also have the ability to be worked on. So we would develop all the interfaces. And I started work, that work, we were very successful in correcting the aberration on the Hubble. And that led to the development of this test bed at NASA to do a lot of the restudies that we used to do in back rooms and wherever we could do it to get that information. And it was all done by hand calculation. And this is the Hubble Space Telescope, and that's Story Musgrave, and this was his first work. This was from the Canadarm from the shuttle. It was brought into the payload bay, and he was able to do a lot of the corrections, and as I said, there were 4 other missions to correct other things. And it's the real beginning of knowing how to design things on orbit to be serviced, which hadn't been done previously. And it was a big change. And the reason it was a big change is something I'm very proud of. I led a team that developed the Robotic Systems Integration Standards. Our contract with NASA was to apply lessons learned underwater to on-orbit operations. So the theory was that we knew what we were doing underwater. We should be able to take that and apply that to space station on-orbit operations. And the theory is correct, because you look at things probably in a different and more practical way, and then we could advise the manufacturers of the systems on how to put in interface and tooling and be able to have a robot come to it or a robotic arm come to it and take it apart and fix it and then put it back into space without letting it get destroyed or having to bring it back at great expense. And you've probably seen a lot of the pictures of Hubble that Hubble has given, some amazing views of the universe. And I started looking up at that point. To me, space became my obsession. So here we have, and this is where designs start to come together. So we talked a little bit earlier about pressure, the effects of pressure. If you have a man in a suit, like here on this side, you're dealing with all these seals. So you have to be able to move your arms, and you have to be able to do those things under extreme pressure. And that's hard to do because seals get pushed together, they stop working, so you have to have special designs to do that. The same is true in space, but the opposite is the case. They operate under less pressure, so they try to balloon up. So you see EVA suits, you'll see there's flexible suits, and if you overinflate them, they become hard to use, and their gloves become hard to use, and that's why they keep the pressures lower. And you'll see throughout the years, these two designs start to converge. We design this to withstand pressure and this to hold pressure. And yet the design ends up looking very, very similar. So can anyone guess which one of these is a spacesuit? Neither of them. This is the more modern designs, newt suits, high pressure suits. These are rated. But you'll see the big difference is on the end effectors. You see no hands and no gloves. Because under great pressure, there really is no way to allow your hand to operate in that environment. So you have to have some kind of dexterity, and it's usually a machine. And we start to develop more and more machines to do our work for us. And it's sort of the philosophical question is, well, you know, I always wondered when two machines, one from an alien species and our machine, meet, what do they say to each other? You know, how do they communicate? And is that really explored? But given time and distance, maybe that's the only way we have to go. So why is that important? Well, here gives you a good idea. Looking at the underwater world first, you'll see submarines operate around 3,000 feet, and then dolphins and killer and whales, and then walruses and sea mammals, and then sperm whales, and all the way down. This is the Trieste, and I'll talk about that in a minute, that went down to the deepest part of the ocean, which is about 36,000 feet, about 16,000 pounds per square inch on every inch of that hull. And that was done, well, we'll talk about that in a minute. Compare that to a whale. There was a record just set or just discovered by a Cuvier-beaked whale, which dove to almost 10,000 feet and was underwater for over 2 hours. So how does that happen? Because if we do that, you can imagine our lungs just will crush, and we don't have enough oxygen in our system to survive. Well, they have higher hemoglobin and higher myoglobin. These are ways of holding oxygen. They can hold oxygen for a huge period of time, over 2 hours and to depths of 2,000 feet. They also have mechanisms where their lungs aren't actually exchanging gas. They're crushed down. They have plates that protect the alveoli in the lungs, and they actually don't take oxygen from their lungs. They take oxygen that's stored in their blood in the myoglobin. It's a protein in the body of the whale. We don't have that. We have somewhat of an adaptation to that, but we don't do that. So when we go down, remember I said every 33 feet, what happens is that the pressure at 30 feet halves the amount of oxygen you have in your lung. Another 30 feet, it's a third. So you can imagine how you start to really compress without having the ability to have oxygen. You won't survive much farther. And the opposite is true. When you go up a mountain, the pressure gets less. And the higher you go, the less pressure you have. But then you start to run out of oxygen. You get sort of neurological responses, you get blindness, all sorts of things can happen to you. Some people are much better at adapting to higher pressure, higher altitudes, lower pressures. And it takes a while. In some places where people live in high mountain altitudes, their hearts are bigger. They can store more air. They've adapted in some way to those heights. So freedivers, we have guys who try to set records all the time. So they want to see how deep they can go and how far they can go. So the current record is around 800 feet at 22 minutes. And the way they achieve that, and this becomes important to the rest of our discussion, is that they pre-breathe oxygen, which oxygen is toxic to human beings at about around 30 feet or lower. And they've had some deaths, they've had some injuries, and yet they continued to do that. But they're really countering their own physiology by doing that. And some are successful and lucky, and others not so much, unfortunately. So we try to design machines, perhaps, to take us out of the loop, to take the humans out of the loop, and design sophisticated machines to sort of mimic us. And we're sort of successful at that. But when it comes to exploring, I still feel that it should be a man who goes there. And I hope that we will be able to design things that will allow us to do that. But unfortunately, given this narrow pressure band that we exist in, that's very narrow. So going to other planets, going to other places in space, this is a big issue. So we brute force our way into things. We build submarines around ourselves, or big metal machines to hold our pressure in or hold our pressure out, and we look through little portholes, and that's basically been the history of diving for the last 4,500 years. And there's all sorts of different times. There's an Egyptian who designed a bellows to pump air to himself so on his snorkel, because if you ever try to take a garden hose and go to the bottom of the pool, it doesn't work. Don't try it. Don't do that at home. So why do we, why do we have the space station at 14 psi, standard atmosphere, and EVA at 8 to 10 psi? And the biggest reason is that the equipment on space station doesn't react well to lower pressures. The dielectric constant, the ability for things to transfer heat, is affected. The equipment is designed at 14.7, built at 14.7. It doesn't work very well when you change the pressure, even slightly, particularly with sensitive electronic equipment. It has a problem doing that. So that's the biggest reason why the whole space station is pressurized at standard atmosphere and pressure. And we talked a little bit about why going EVA is important to lower the pressure. So what do? They take upwards of 3 hours to pre-breathe. I don't know if you've heard of that as a regimen, but basically when an astronaut does extreme exercise, with the idea to try to purge himself of all the nitrogen that he's been breathing, and breathe pure oxygen. And that takes about 2.5 hours just to prepare to go through the airlock to work out in space. And then coming back is a similar issue. So you can imagine there's a lot of focus on trying to find ways to eliminate the pre-breathe, because the cost would be prohibitive to build equipment that would survive in the lower pressures. And it's that sensitive, and that's the real reason why we have this big difference. This, I think, just illustrates the point that I talked about before. This has no hands. This is a spacesuit developed at Ames, and they still have the problem with the dexterity. Even at trying to keep that at a standard pressure, they still can't find a way for a hand to work as it should properly work, or you'd like it to work. And so a lot of focus is on that. The bigger focus is obviously to eliminate the pre-breathe requirement. And actually a guy I used to work for at Deep Oceaneering Space Systems, and by the way, I forgot to mention, I became general manager of Oceaneering Space Systems with this work. We worked with Ames, and the guy that I worked for actually became an astronaut, and he was on 2 missions, and he now runs this pre-breathe, because we would all sit around as divers and go, well, why do they do that? It makes no sense. And it really doesn't make a whole lot of sense. You heard about the Apollo 1 fire, and when they used to use pure oxygen, which is a really dangerous thing. Everything ignites in a pure oxygen environment. And so a lot of guys put themselves at risk until the Apollo 1 fire sort of drove it home that you have a real problem with oxygen. There's really no reason to breathe pure oxygen that way. And there are things that we're talking about. One is perfluorinated carbon, which is a fluid where you can actually breathe a fluid that has oxygen in it, and hopefully that will help you equalize pressure. So if you saw The Abyss, you saw the guy filled it up, right? It's kind of science fiction, but they actually have had mice breathing this chemical and having gas exchange. It hasn't worked so well for humans yet, but it's research that's ongoing. Now, I know some of you wanted to talk, Donna told me that you wanted to talk about the Liberty Bell 7. So one of the last projects that I worked on, which is the recovery of the Liberty Bell. It was piloted by Gus Grissom, who was, tragically, he died in the fire, the Apollo 1 fire later on. This was his mission. It was a 15-minute mission, and you probably know the story that when he, this is the capsule going up, and I'm sorry, I'm trying to go fast. This is his capsule. When he landed, when his capsule landed, he had already disconnected his oxygen tube, and the hatch prematurely blew off. And there's a lot of controversy. People will talk about, well, you know, he did it himself by accident, and there was a big inquiry about it. It was a big controversy at the time. But what actually happened was that it blew off, and the capsule started to sink. And because he had disconnected his hose, his suit started to fill up with water. And he was scrambling out. There were divers there to help him out, but the spacecraft filled with water, and the helicopter couldn't hold it. It started to get metal chip warnings in its oil, so the pilot released it and it sank. So a friend of mine, Kurt Newport, who conceived of the idea that let's go find Gus Grissom's capsule. And it was a cool idea, so let's go do it. And it took a while. My big claim to fame in that project was that I got Discovery Channel to fund it. That's my one major contribution to this project, was I closed the deal in the hallway. And I felt pretty proud of myself at the time. And so we hired Oceaneering International, which is the company that I work for, Oceaneering Space Systems. And this is a towfish. This is a system that you use. You tow it behind a boat at a certain depth, and it uses sound to give you a picture of the bottom, and you can identify where things might be. And then you send an ROV down to do it. Now, the interesting part is that where the capsule went down was at the Andros Island Lake Basin, and that's the original search area. It's got a lot of crevasses. The spacecraft itself, when it fell to the bottom, actually fell at the top of a plateau. Probably 10% of the whole search area, we could have found it, and we found it there, and it was pretty amazing. So now we got to go get it. So we take an ROV, a remotely operated vehicle with all the robots and all the stuff that I've been talking about, and we send that down to the bottom to attach to this, because this is what we saw for the first time. As the ROV came up to a point that we had identified, that was the capsule loomed into the light. And you can imagine all the screaming and yelling and excitement, because it was absolutely unexpected. And it was really an exciting moment. It's a titanium hull, so the titanium survived. Now, what we were hoping we'd get the film back, because in those days they used film of the flight. It wasn't recoverable, but we were really worried that on the spacecraft itself, it has something called a SOFAR bomb. It's a ranging bomb, and it's designed to tell you where the spacecraft is when it sinks. That it was built into it. It's a barometric bomb, and it does a low pressure wave, and they can hear it and pinpoint where the vehicle might be. The second one never went off, so we knew it was on there, and of course, young, foolish guys that we were a little worried that it might still be armed. And we were afraid that when we went up to the capsule, if we touched the capsule, it would go off. It didn't, fortunately. It wasn't working. But we had to calculate where that landed by the drift. So we knew where it was on the surface of the water, but taking old meteorological data from 1961, whatever it was, we had to find the drift. And we were pretty good at it. I'm kind of proud of those calculations, because I did a lot of them, and we found it. I'm quite proud of that. This is the capsule after it was taken out of the sea prior to restoration. And this is the capsule restored. It's at the Hutchinson, Kansas, at the Kansas Cosmosphere in Kansas. That's where it's on display. Kurt and I had a bit of a disagreement because I thought it should go to the Smithsonian, but Discovery paid for everything and they wanted it to go to Kansas, so that's how it happened. And it goes on tour every once in a while. It just came back from Europe and they take it on tour. This gives you an idea how big it is, right? So you can imagine being strapped into this little thing that's not much bigger than a forklift, and when they talk about lighting the candle under you, that's really what happens. It's kind of interesting. I always love this picture because of the scale. It's the same technologies that I guess the last job that I consulted on with Oceaneering was Flight 800. There was about 120 feet of water, and we used ROVs and divers working together. Robotic machines working with divers, and it was well orchestrated. It was really wonderfully done, and it was one of the hardest things I've ever had to do. There was a lot of pain there, and anyway, we'll move away from that. So the iconic footprint. I'm sorry. Yes.
And I have a question. So for the flight you mentioned, what about the flight 370 from Malaysia? So
they worked on that too, but I wasn't part of that flight. And my suspicion is that it sank into a crevasse. It's almost impossible to, hard to find unless you come on it. And I'm sorry they gave up on it. I think they should continue to do that because serendipity works, persistence works, and they should be able to find it if they kept at it. But you can imagine.
Is there a certain time period, like with higher chance to locate the residues?
Well, the changes in sonar technology, so more angular impressions that you can take, or signatures that you can get, it's advanced more since the flight loss, and I think it's definitely worth going back. The technologies have changed a lot. I'm working on something right now using light as opposed to sonar as a means to do exactly that. So I think it is findable, but the search area is so huge and the politics involved are incredibly problematic. That's one of the things that stopped the searches. Yeah.
Yeah, in the case of Freedom 7, because it was basically abandoned, did salvage rights apply?
Well, that was the argument we made because NASA made a claim on it. Yeah, and they lost because law of the sea did prevail. The actual litigant in that was the Bahamas, and they had no claim on it, and they allowed it. They allowed us to do it, and I think they should. That's the problem with litigation, isn't it? People fight over stuff. You find a lot of treasure hunters have that same fight off the coast of Florida, in particular. A lot of that happens. So this is where I'm going to make my plug for our planet, because we've looked at a lot of our planets. We've looked at a lot of our orbital bodies. We have one footprint or set of footprints on one body in our solar system, and that's the moon. And we're lucky to have a gentleman with us here tonight who worked on the LEM program. And I think we've stalled. And if you think you're going to find another habitable planet, you're not right now. So you better take care of this one. And that's my plea for taking care of this planet, because that's really the reason why. We don't have machines that are going to take us where we need to go if we screw this up. Excuse my language. So talk about that, going to Mars. This was the first Viking, first robot on another planet. The robot was this little guy. It was a soil sampler. You're probably all aware of that. I won't spend a whole lot of time on it. That's the first planet we landed something on, got some samples. We've had subsequent missions, as you know. Also the Voyager 1 and Voyager 2. Oddly, Voyager 2 took off before Voyager 1. I've never understood that. These are the first spacecraft that have gone out into interstellar space. So in the 70s till now, just last year, Voyager 2 crossed the threshold into interstellar space. That starts to give you a size of the universe and how big it is, and how are we going to explore these things if it takes a billion light years to get to where you want to go. And it's a sobering thought, I think. So on Mars, you're all aware of this, Spirit and Opportunity and Curiosity. We did some work with JPL on some of the algorithms for how this machine will work over obstacles. Mars is a problem. Just our near neighbor Mars is a 30-minute round trip in communication. So you can't just sort of sit here with a joystick and drive it around. You got to send it a command, wait for 15 minutes, and then get confirmation that it did what it did. And it's like watching paint dry, you know. So a lot of people, Edmund Halley, the astronomer, discovered Halley's Comet, returns every 76 years, I think it is. A lot of people don't know. So I was looking, Donna, for crossovers between space and deep ocean. Well, here's one of the great ones. This is Edmund Halley. It's known for the discovery of Halley's Comet, but what you don't know is that he was the guy who really modernized the modern diving bell, like in 1714. So what we talked about a little, was when you take a bell and you have air in it, right? As you lower it down, the water pressure keeps compressing it. So in 30 feet, it's half the volume of air you had in it. Another 30 feet, it's a third the volume of air you had in it. So you can't really go too deep by just putting a diving bell down. You run out of air really quickly. So he came up with an ingenious idea in a time when there's no such thing as a compressor. There's nothing like that. He said, well, why don't I put barrels outside the bell, and they're subject to compression. And he put little bung holes here, and as that air compressed, he would then just deliver that air back into the bell and increase. So this is like the first scuba tank, you know, in a way, right? It's kind of cool. So today's scuba tanks are about 3,000 PSI, and they hold about 72 cubic feet of air, which is about 5 by 4 by 3 cube, kind of. That's enough air to breathe for, you know, if you're good at it, 45 minutes, depending on your depth. And back in 1700, he invented something really similar to that. And I always thought that was cool because he was more interested in the ocean. And it was just an aside that he discovered, he did the math to get Halley's Comet to come back. Oh, and this was his design, or theoretically this was his design. So instead of having a bell, you'd have less space, but you'd have more air to put into it. You could last longer underwater. And I love that about people who think outside the box and come up with these really great solutions to do things. Talk about solutions that aren't so great. This is the Turtle. This was the first submarine ever designed for warfare. And I just wanted to point out a couple of things. The idea was that they would take that Turtle and they'd go over to that ship and they'd try to drill a hole through the bottom and sink it, or attach a mine to it and blow it up. Not too successful. And one of the reasons it wasn't too successful is that this is the propeller. And it's not like a propeller that we know, and I can't imagine how it would have ever worked. But they did manage to make contact with an English ship once. There's not a lot in the record about what actually happened, and I don't want to speculate. So the first diving systems, as you see, resemble EVA systems, right? What we do out in space. These are sort of people's ideas about things before they've actually experienced it, and they modify it and they change it and they learn and they do all those cool things. The interesting part about this is that this is based on an accident. The accident was a fire that occurred in England in the 1700s, and they were trying to put the fire out, and they had they pump water, and this guy got this great idea. He ran next door, he got a medieval helmet, and he put it on his head, and he said, don't pump water, pump air into my helmet. And he ran into the fire and they were trying to save horses. His name was John Dean, not the Watergate John Dean, not even a relative, but that was one of those moments of inspiration where he had moments to think of something and he just thought of that. It just came to him. I just think that's cool. And a lot of the things that we take for granted here, a lot of them are invented that way. It's based on a need or an urgency to do something. And think about this, you are a generation the first generation in humankind that has at its fingertips all the knowledge, most of the knowledge of the world. We've never had that before. And it's a big responsibility, what we do with it. We can do good, we can do bad. William Beebe, he's well known. Chris, you probably know William Beebe because he was the first biologist to take a bathysphere and go down around 500 feet to study animals, marine animals in their natural environment. And he did a whole bunch of dives on that. And to me, that sort of, it describes a difference. Either you're going to have warfare or you're going to design to explore. And I think the best part of us is exploring and finding life and doing those things and learning more that way. This is the Trieste. This is the first submarine. Oddly enough, a year before Gagarin's flight, Yuri Gagarin was the first guy in space, a Russian. This was a year before that. And this is actually a gasoline-filled ballast tank. Because at those depths, we talked about the crushing weight of water. If you have air in there, that would just crush that down at 16 psi. There's not much that can hold it except for this little bathysphere that's underneath. And once they would go down, it was weighted, and once they hit the bottom, they would come back up. That trip took about almost 5 hours to the bottom. And I found some of my father's notes, because this was actually funded by Grumman, Jacques Picard and Captain Walsh. And in the notes, there was a note that said, after the sediment settled when they hit the bottom, there was a Coke bottle that they observed outside a porthole. I always thought that was such a prophecy of things to come. This is inside, so if anybody's claustrophobic, and I've been in situations, a lot of situations like that. I didn't develop claustrophobia until I took an MRI. So, this is Jacques Cousteau, my childhood hero. This is a thing called the soucoupe. This is, if any of you watched his shows, which I did avidly, this was his submarine that he went down and explored all and came up and said, "They are marvelous, they are wonderful, these things." You know. Here's a little known submarine. It's called the Ben Franklin, also funded by Grumman. The private partnership between Grumman as a defense contractor and exploring the outer edges of both the universe, space, and underwater is kind of phenomenal in their history. They funded this project. This was called the Gulfstream Drift Project. It was actually undertaken by Auguste Picard's son, Jacques, who's standing there. And what they did was they launched this in the Gulf Stream and then let it ride up and down, traveling the Gulf Stream for 30 days, and then surfaced in Halifax. And the idea was to study the Gulf Stream, all the critters that went along the Gulf Stream, and characterize the Gulf Stream in ways that nobody has done since. Although he wants to. That there is his sea orbiter. That's the little top part. That's this right here. He's built this. He's looking for funding, if anybody's at all interested. So back in the Marianas Trench, there we go, the deepest place. To describe how deep that is, if you took the Mount Everest and put it at the bottom, you'd still have 1.5 miles from the top of Mount Everest to the surface, to give you an idea of how big the ocean is, and then how unbelievably huge the universe is. This is Alvin. This is another submarine. The reason this is from Woods Hole, this was originally conceived by Bob Ballard. This was the first discovery of another life form on our planet. And that was a discovery of life based on hydrogen sulfide, not on light. And it's really cool. Now, off the coast of the Galapagos, about 8,000 feet, they find clams with hemoglobin. And they find these most amazing life forms that don't need light to live. That gives you pause that life really does persist in the most amazing places. And where will we find it when we finally are able to find a way to travel farther and faster? So we keep, and I haven't been referencing my notes, I apologize. It's coming out of my memory, but there are some points that I did want to make. Wow, I moved along. I don't know what time it is, but I'm almost done, guys. So on Earth, we continue to explore. This is a towfish that we described. So an estimated 50 to 80% of all life on Earth is found under the ocean. And the oceans contain 99% of all the living space on the planet. So less than 10% of that space has been explored by humans, and 85% of the area, 90% of the volume constitute what we call the deep ocean. So while we think we know a lot, we don't know that much. There's a lot to explore up in space and also underwater. So what are we going to do? We find life almost everywhere. What about in space? Well, there's something called the Drake equation, which some of you know about. It's kind of it's a conjecture about what species, what civilizations will develop radio in order to communicate. And I submit that communication is through light, not through radio waves. On planets that have fluids, radio waves don't penetrate, not on any frequency. But light penetrates almost everything. So it's something that I'm working on now with my company, and I'm excited about the possibilities. So my other vehicle's unmanned, and that gets back to what happens when we send a machine out and it meets another machine from another civilization, and what do they say to each other? How do they communicate? How do they represent each other? Voyager went out, it has a record, gold-plated record, and has pictures of us, and I don't know if another species looked at that, whether they would make sense out of that or not. So how do we communicate? And that's kind of an interesting question. Are we really exploring if we send machines out, and what do they do when they meet each other? I just don't know, but it's kind of fun to think about. So why are we driven to explore? For me personally, it's for this reason, that we see the persistence of life even in very hostile environments. It's amazing. Everywhere you turn, there's life. Everywhere you go, life everywhere. We expect to find life as common in our universe as we find it on our planet, but so far we have not. That's disconcerting to me. So in our solar system, we haven't found anything. And it's easy to give up and turn around. But we need to re-energize our space program. We need to re-energize our curiosity. We need to re-energize our desire to go out in space, go out and search, go out and do the things that are truly human. Not for war, not for any other purpose, but to drive our curiosity and explore and discover and become part of our universe in a better way than we are now. Because our nature has consequences. What we do has consequences, and I think we're all aware of that on this planet. So we find life at the surface of our ocean. We find life at the bottom of the Marianas Trench. This is a snailfish that was recently discovered at 36,000 feet underwater, happily minding its own business until someone gave it a flash, and I have no idea if it got blinded or what happened, but it's probably still remembering that experience. We find life that's based not on photosynthesis, but on the consumption of sulfides, which is really cool. And we find life at the top of Mount Everest. This is a Himalayan jumping spider. I often wonder what it was jumping on. But it's right there at the top. It's right there at the very top, at the outer edges of our atmosphere. So we have something called the Armstrong limit, which is if you start to go up higher and higher and higher and higher, you get less and less pressure. And at about 50 to 60,000 feet, essentially water will boil, your blood will boil. You cannot survive it. You will literally boil in place at 50 to 60,000 feet up with at almost zero pressure. About 2 to 3 psi, you really begin to, you won't survive it. And it's the whole reason why we have spacesuits, why we do all those things. And conversely, going all the way down to the ocean, you have the same thing happening to you. But the Armstrong limit is, you saw in the movie The Martian, or I think one movie where some guy boiled in his spacesuit because he got exposed to the vacuum. So when you got exposed to a vacuum, if I had a balloon here and it suddenly became a vacuum, the balloon would keep expanding until it broke, and it will keep on going. And that's the problem that we have, the physiology of that. So my dreams came true. And they came true because of people like many of you in this room that make an impact on others. And I had some really great people that made a huge impact on me. And I thank you because I hadn't had the opportunity to go through this part of my life until now. And I certainly appreciate you all listening to my stories. I have lots of sea stories which I refrain from repeating, but harrowing moments at sea and all those kinds of things. But I was very blessed to have parents that let me do everything I want, including setting their basement on fire and having bees in my bedroom. But please let your kids follow their passions, because mine did. And thank you very much. And if you have questions. So if you have any questions, please ask. Yes?
You mentioned that you thought life might only be discovered in other parts of the universe. But what's your belief about the satellites of Jupiter and Saturn that may contain oceans that might require drilling to explore? This talks about water beneath the surfaces, talks about methane beneath the surfaces. Do you feel encouraged that perhaps your experience with deep sea diving might be translatable to a probe that might be sent to drill and explore those oceans?
Absolutely. It's not Ios, or maybe Ios, but there's one moon that has liquid methane on it. Where that methane came from. On space station, we get oxygen actually from water, that we bring up, that astronauts bring up. And then you use electrolysis to separate that out, hydrogen, oxygen. Then you take that hydrogen and you combine it with CO2, you get water back again, you get methane. So methane seems to be a component in that. So I'm encouraged by that. Whether we're going to find civilized life or however do you define that. I always used to think that maybe whales were the smartest thing on the planet, and we were just part of an experiment that they were conducting. But I have a lot of hope that we can. But even so, we still have the issues that how we treat our own planet. And those are lessons that we hopefully will take with us when we begin to grow and go out into space. So I'm positive. I'm always optimistic that we'll find life. Yes. Yes?
John, you had mentioned that a 1 gallon per minute oil leak was an acceptable rate. Have we had any advancements?
I certainly hope so. I was kind of a pain when I dove, because when I saw things like that, so I got sort of, I think, labeled as oh, here he is again, he's pointing this stuff out. Certainly the technologies have changed a lot, but the BP accident is a perfect example. Things can go wrong, and we need to be able to respond to things going wrong. And right now we have the possibility of oil being drilled right up 3 miles off our own coast. We need to be cognizant of that, and because you can't see it doesn't mean it's not there and not happening. Yeah. Yes?
Are diver suits and astronaut suits today made all in one piece?
No, well, they have to be flexible, so they're not anymore. The new Ames versions of them have slip fittings, so it's sort of a rotating seal, so you can move your arm around like that. The current EVA that's used on space station are still sort of the flexible kind of suits that you have, and it's one of the reasons why the pressures have to be lower and why pre-breathing to go do EVAs, it requires a 2.5 hour time investment. It's also a way to purge nitrogen, because for some reason they think you're going to get decompression sickness when you come back on space station, and that's not something we in the diving world have experienced. So it's a little more complicated than that. There's some of the partial pressures of gas and things like that, but that's where they're headed, is that way. Yes?
West Hampton Beach, there are these strange, multi-pillared things out in the water of the ocean. Are those oil well drilling things that are going to be used in?
I'm not sure what you're referring to.
They're like maybe a half a mile out. You can see them from the beach itself, and they're spaced maybe a quarter mile apart, and they have like 4 pillars and there's all kinds of metal. It looks like something out there. You can't quite tell what it is.
It could be a dredging unit. I don't know because
Things like that before any other beach anywhere.
yeah, the Bureau of Ocean Energy Management continuously drills for sand. Sand is a commodity that's rapidly being taken up. You know, faced with sea level rise and those other issues, sand is becoming a commodity that has, you know, great value. You know, we work hard to protect our coasts, and you use sand to do that, but you constantly have to replenish it. And it's a serious issue to consider. I suspect that's what it is, but I don't know. But I'm going to go down there tomorrow and see.
Things like that, we scoop sand up from the bottom pool, we can fix the thing that's in there.
Yeah, I'm assuming it's a dredging operation, but I don't know. I know they have contracts sort of west of the bridge, the second bridge coming out of West Hampton Beach, down in that area where, you know, where the jetties are. That offshore they do have some sand replenishment projects that go on. Yes, Bruce.
The other day you described an illustration of what happens at great depths involving a styrofoam cup.
Oh, I forgot all about that. Thank you. So I have it's an interesting. You know, we passed a law in Southampton to ban styrofoam cups, so I couldn't find a styrofoam cup. But I do have a cup of this size. And if this was styrofoam, when we were on the Titanic, a friend of mine, Kurt Newport, that I talked about before, we used to take the styrofoam cups and take them down in the ROVs and then bring them back. And when we bring them back, they look like this. And it really illustrates the effect of pressure and what happens, because polystyrene has little air holes in it, little air bubbles in it. That's what it's called. They call it expanded polystyrene. So normally it looks like this, but you take all the air out of it and it looks like that. And this is from the Titanic. This is actually from the Titanic, not from the Titanic, but from the basket on an ROV that was taken down to the Titanic. But it's a good illustrator. Thank you, Bruce, for reminding me of that.
But that doesn't deteriorate, does it, John?
This, no. As a matter of fact, in its expanded form, it makes up about 30% of the global landfills. So there's a good reason to find other ways of doing things. This was a coffee cup that was given me today. This is actually paper, but it's reusable. You can keep using this over and over and over again, which is very cool. So the thought, people are taking responsibility, using their imagination and their skills to respond to the needs that we have to protect this resource, particularly out here, how beautiful this place is. You know, you have a whole university dedicated to the study of the marine sciences and the atmospheric sciences, and that means something. And they learn a lot, and we need to learn from them. Yes?
Hey, John.
Hey.
Thanks for the lecture.
Sure.
I don't remember if it was Ballard or Cameron who was in an ROV, and you know, something was pointed out to him that the other individual was looking at through a porthole, and he was staring at the computer monitor and he sort of had this aha moment of, why exactly am I down here when, you know, I'm staring at this screen. So I wonder about the idea of not putting our physiologically limited selves into the equation and relying more on remotely operated vehicles.
Well, I think we do, increasingly we do, but it's just plain fun to be there, you know? And your observations in a sort of a three-dimensional way, even through a porthole, is different than I find from a screen. And I think it evokes a certain emotion that's important to exploration. And that's my feeling. But it is just a lot of, although sometimes when you're in a sub and you get down, you know, a few thousand feet and you hear a loud bang or a clang, you kind of reevaluate that statement. Thank you. Yes?
John, speaking of Gus Grissom, is there truth to the story that he was loaded down with dimes in his pocket
that he took into space with him?
I've heard
that he had some trouble.
We found no dimes. Yeah, found no dimes unless unless he ditched him or something. I don't know. It was, he was a great pilot. He was a great guy by all accounts, and it's kind of sad that that was attributed to him. But that capsule. He was brave to fly it because when it was delivered to Canaveral, the flight controls were reversed. There were problems with it. They fixed sort of overnight. It was that kind of environment at that time. Yeah. Yes.
John, your admiration for the preservation of our environment is great. Have you ever visited the Pacific Gyre or the so-called floating islands of garbage?
I have. I was in the Pacific Gyre several times, actually in 1972, 73, and at that time it was very noticeable. We weren't even sure what we were seeing. It was almost 500 or 600 miles wide, even at that time, and it spins slowly at great depths. It's particles, little pieces of plastic, essentially, that's what it is. And and we talk about it. I think Maria can probably attest to that too. That
5,000 feet deep, they're finding those particles inside fish.
Yeah, and inside, yeah, exactly. And so the fish eat it, and so we eat it, and it's a big issue. There's an estimate that I heard. I don't know how true it is. I'm not going to promote fake news, but there's an estimate that by volume, we're going to have more plastic in the ocean than we will fish by 2040. So it's one of these out of sight, out of mind things that we don't really deal with, but you can. You can do things like this and not throw plastics out and be more responsible. It's no one's fault, except it's all of our fault. And it's only our fault if we don't do anything about it.
Unintended consequences.
Yep, and there are a lot of those. We're human beings, but if we don't react to our mistakes, then I don't think we're being true to ourselves. That's a somber note, but it's an important issue. No more questions? Thank you. Oh, I did okay, Tom. Thank you.
Thank you all for coming. We look forward to seeing you back here April 5th for the State of the Bays Symposium. If you haven't already, we have a sign-up sheet for our email. We can alert you. We give 4 lectures every spring semester, 4 lectures every fall semester, and many of them almost as good as this one. Thank you for coming. Have a great
Well, I
weekend.
realize I'm like a half an hour short, so I must be sorry. Really?